Hello, good afternoon, good morning. My name is Chiara Benetti and I welcome you on behalf of ETA Florence Renewable Energies, technical organizer of this webinar. Today's webinar is entitled Mixed Plastic Waste, Sustainable Valorization Solutions for Material and Energy Recovery. The webinar will be introduced by Mar Edo, researcher at Research Institutes of Sweden and IEA Bioenergy Task 36 leader, and will be moderated by Dieter Stubbs, professor at Karlsruhe Institute of Technology and IEA Bioenergy Task 36 country representative. The speakers of the webinars will be Marco Tomasi Morgano, CTO at Arcos Green Cycling Technologies, Rikard Janssen, development engineer at the Sweden Plastic Recycling, Henrik Thunman, professor and head of division at Chalmers University of Technology, and Salar Tavakol, PhD in chemical and process engineering, head of pyrolysis technology at the Institute for Technical Chemistry, Karlsruhe. As usual, you may drop questions during the webinar by using the Q&A tab that you can find at the bottom of your screen. Our speakers will reply to your questions at the end of all presentations by replying live to your questions, or they will have the opportunity during all presentations to reply to your question by writing the answers in the opposite tab. Please do not use the chat box for questions, but just the Q&A tab. The webinar is recorded, and the recording and presentations of the webinar will be available in the next few days on IEA Bioenergy website. That's all from my side. I'll give the floor to Mar Edo and enjoy the webinar. Thank you.
Thank you, Chiara, for this opening. Hi, everyone. I would like to welcome everyone to this webinar on behalf of IEA Bioenergy. My name is Mar Edo, and within IEA Bioenergy, I'm leading Task 36. That is a group of experts that focuses on the effect that initiatives along the waste energy value chain have in the deployment of bioenergy. And finding sustainable solution for handling plastic waste has already been a relevant question for many years due to the volumes of plastic generated worldwide and the impact that it has on the environment. If we talk about mixed plastic waste in particular, its heterogeneous composition poses an extra challenge, and for that reason, it might end up being incinerated or landfilled, losing with it resources and impacting negatively the environment. So in this webinar, we would like to bring light to technical solutions that lead to a more sustainable valorization of this waste stream. So with this, I would like to thank you, all of you who are participating in this webinar. Thank you for your interest. I want to thank in advance all the nice speakers that we have, very knowledgeable. Thank you for sharing your expertise and knowledge. And I wish you a nice seminar. I will leave the floor now to my colleague Dieter, who will moderate this event. Thank you so much.
Yeah, thank you, Mar. Thanks very much for the introduction. Hello, everybody, also from my side, and welcome to this webinar on advanced technologies to realize circular economy. And we will focus on mixed plastic waste, so the valuable but not very much recycled fractions, and have a look at technology options, all kinds of advanced technologies that might help us in creating a circular economy and avoid incineration or even landfilling of valuable plastic materials. So we will have 4 contributions for different presentations from colleagues from Sweden and Germany in that case. And the first presentation will be given by Salar Tavakol from Karlsruhe Institute of Technology in Germany, where he is leader of a research group on plastics pyrolysis. Now his focus will be on avoiding incineration of mixed plastic waste. Salar, I'll give the floor and the presentation to you.
Thank you very much, Dieter. Hello, everybody. I'm going to share my screen and start the discussion. So, all right. I think it should be correct now, right?
No, it's not in the presentation mode, but in the...
Okay.
It's correct now.
Perfect.
Yes.
Thank you very much. So once again, thank you everybody for your attention. I'm going to talk today about the alternative pathways to incineration of mixed plastic waste for the contribution to circular plastics in order to close the carbon cycle. Greetings to you from Institute for Technical Chemistry, Karlsruhe Institute of Technology in Germany. This is the future perspective of plastic life cycle. As you may see, this is currently the linear life cycle in the carbon economy, what we are using the resources to produce our products, and after usage, we use the energy recovery, which is the perhaps more established method. At this moment, more and more mechanical recycling and carbon capture utilization become important due to reducing of the usage of resources, but also reducing the carbon dioxide emission. But a very important part to this cycle will be basically the chemical recycling of plastics, especially to solve the waste problem, and on the other side, to solve the critical raw material problem that we do have in the world. On the other side, the bottleneck of chemical recycling of plastics will be the scale up of mixed plastic plants in chemical recycling, which has to be considered and has to gain momentum at this moment in order to have the carbon circular economy cycle in the most efficient in the value chain. So I just brought two different examples for you today to show. One of them will be the circularity of organic rich fraction from the automobile industry, and the other one will be the post-consumer waste. What you're seeing here is just a small mass balance from the, let's say, representative study from Germany, which can be, of course, different in different countries and different generations of automobiles, and also if in different generations and different locations of shredding. But let's just keep it as an example and take a look at it. What we see here in the first stage of manual dismantling, we lose 10% of the material, which 6% of them can be recycled mechanically, let's say the glasses, the tires from the car, and so on. Only a small part of it can be reused, and smaller fraction will be burned in incinerations. We have a small loss in this stage, and we have the other stage in which we are getting 60% of the, let's say, entire mass of the automobile as metals out in a quite efficient way. Then we have the shredding stage, which 14% will be the shredder light fraction and 10% will be the shredder heavy fraction, which actually the name shows. The shredder heavy fraction contains less than 50% of it, so from 10.1% and 6.2% metals, and it has smaller fraction of non-metals. Quite easily for the metals, the mechanical recycling, and then it stays the rest for the thermal treatment, let's say mostly plastics or the other ways. When we look at the shredder light fraction here from 14.1%, basically only 1.1% are metal, and we have the dominant weight of this fraction as plastics usually. which you can see a smaller fraction can be recycled mechanically, and we have dominantly, let's say around 9% of this 14% is at this moment will be incinerated, which I think there can be a much better way of using these resources. So now we've looked, we may have 27 millions of cars each year sent to shredding plants. And if we imagine each car might be 2 tons of the weight, now we are talking about more than 9 million tons of mixed plastics only staying after the shredding. So we are talking about a huge amount of resources that can be used and can become back to our cycles. The funny part is that people saying that more than 90% of the cars are recycled today. But the point is that they are the metal parts, which is the easiest part to recycle. So the low-hanging fruits are already harvested. So now we have to concentrate for recycling of the plastics in a meaningful way from such a very varietyful fraction. And the point is that we have so many different polymers mixed, functionalized, and will be used in automotives. And the point is that will it be easy to have a dedicated specific different polymers, numerous different fractions, and try to reuse them, or let's say separate them from each other? Or is it easier to have a couple of specific mixed plastic based on their polymer content and contamination contents, and try to use the chemical recycling for recycling them back into the cycle? This is, for example, one of the cases. Talking about the polymer content and contaminations, the sensor based systems are being used at this moment, fully equipped in many of the mechanical recycling plants in Europe and also the rest of the world. And they are quite efficient for polymers which are mechanically recyclable. The problem of mixed plastic waste in most of the cases is the functionalized and flame retardants and additives and fillers inside, which makes the nature of these plastics not mechanically recyclable. On the other side, we have a lot of joints and connections of the metals and plastic with each other, or other kind of combinations such as cable and so on, which is from their nature impossible to separate from each other. So after shredding, we are going to have a kind of heterogeneous mixture of these polymers with other impurities. The future sensor-based sorting systems may have an interesting application not only in mechanical recycling and sorting of the polymers for mechanical recyclings, but also for chemical recyclings, in the way that particle-based analysis, so basically multi-sensor imaging, non-invasives based off the colors, or hyperspectral cameras may use the short to near IR or short waves, IR, mid waves, and even long waves can be applied to identify the type of the polymer, in which we can understand what can be approximately the contamination and types of the polymers which are being thrown in chemical recycling plants. This may help a lot in the future to be able to adjust the parameters of the plants in line based on live tracking of the feedstock which will be used in them. A little bit about these topics we are going to hear from Ricard, and I'm going to go a little bit further and look at the shredder light fraction, what we have seen from the other mass balance. Now this is a specific type of this shredder light fraction, a kind of representative, but as I said, there are different big deviation depends on the locations, the type of cars, and so on. So the question will be what we have done in this study by ourselves. we get a realistic Schroeder light fraction, pyrolyze them, and try to look at the quality of the products by having a closed mass balance, which is already published in this publication. I invite you to read the publication because I'm not going to talk a lot about it because we don't have time. But you will see basically what is inside. So the question is that what is the most beneficial process in terms of climate change impact? This is one of the most important thing that has to be taken care of, has to be considered, especially because the feedstock that we are designing our plants today and we are researching on them are not the feedstock that will be landing in our waste in 5 to 10 years, because the sorting plants are getting better due to improvements in visual systems, due to improvements in AI assisted systems, but also the improvements in the plastics that we are producing. We are going to have a different fractions of plastic waste in the future. So this is very important that we can try to understand, we can try to prognose this future and these fractions in order to design our processes today for this. So coming back to climate change impact of Schroeder light fraction. What I'm showing you at this moment, this is a mass balance of Schroeder light fraction from recycling via pyrolysis. As you see at the very first glance, we have 9% of metal scrap, which shows already a discrepant to the mass balance that I showed you at the beginning. If you remember, we had only, let's say, around 1% of the non-plastic fractions. But this is exactly what I'm calling the heterogeneity of data which are available. But this is from our own data, and this is the mixture that we shredded by ourselves. Quite reliable. What you may see is that from the mass balance of the material, we have got 45% pyrolysis oil, which after hydrotreatment, the rest will be the studies and the assessments. We are getting 42% of hydrotreated and treated, post-treated, let's say, a pyrolysis oil, which at the end giving us 31% high-value chemicals. This is basically one of the things that we are getting from this study, showing us how it can have the entire chain from the waste to the valuable products, which from them it is possible once again to produce polyolefins and the other valuable chemicals. And very important is that the hydrotreatment here is not considered economically in the study, and it might be also other routes available. Let's look once again at carbon efficiency of the same path. So now we are talking about the carbon content and the carbon percentage instead of the mass balance. What we see, of course, the RDF has 100% carbon content because the metal scrap has no carbon, let's say. And from that, we are getting 68% of the carbon landing in pyrolysis oil. And by upgrading that, it is assumed that the carbon stays inside because the hydrotreating is just reducing the contaminations and contaminants, which are now then afterwards landing in the off gases. What we see here is basically more than 50% of the carbon recovery due to the conversion of the Schroeder light fraction to valuable chemicals and products, which basically means we can at least save 50% of the carbon when we go this route compared to incineration. This is an outcome of this study. So now I would like to show you very shortly what will happen if we, instead of pyrolysis, we try to gasify this material. This is basically based on calculations and simulations. This is not done experimentally. But as you may see here, We have the same 68% pyrolysis oil. This is based on our own experimental work. And if we use the entrained flow gasification, which takes the pyrolysis oil as feedstock, we will see that for oxo syngas basically means the same concentration of hydrogen and CO, we are going to get 63% of the carbon in the raw syngas. This basically shows the most carbon content in the pyrolysis can be reserved due to this route, but the rest of the route, let's say syngas preparation and the conversion of the syngas to other chemicals are not considered in this one. So once again, I would like to invite you to see this publication that we have published last year, and you will get more information about that. This was one of the examples that I wanted to show you regarding the mixed plastic fractions from the automotive industries. Now I would like to show you another fraction, another waste, another plastic-rich waste, which is totally different. What you see, this is like the untreated refuse-derived fuels from the post-consumer waste. So they are available, they are abundant in a very huge amount because we are producing wastes, of course. This is basically the remaining sorts after a mechanical recycling plant picked the clean polymers, which might be recycled mechanically. So whatever is used in this study and experimentally is not mechanically recyclable. And this is, of course, not comparable with the other RDF that you have seen from the automotive waste fraction. First of all, the polymer content is completely different, but also the contamination content is different. So they are different heteroatoms in this waste compared to the other waste. So looking at the same route of pyrolyzing this material, this time looking at mass balance. Once again here, we are seeing the mass balance of pyrolysis, hydroprocessing, and steam cracking, so producing the steam cracker feedstocks. We see that 27% mass related, we have the pyrolysis oil. On the other side, we have 11% of wastewater, which was not available in this amount in the other material, and 18% ashes, and 44% of off-gases, which if you look at the carbon efficiencies, in this case, we have, let's say for pyrolysis and upgrading around 45%. So a little bit lower than the other material, but still enormous saving of the resources compared to incineration. So let's say whatever material that we get, what kind of mechanical recycling route that we introduce, you can say resources compared to incineration. Now I would like to show you a kind of comparison of the climate change impact for this new feedstock. The study has been done systematically, considering the entire value chain of the material for pyrolysis and production of the steam cracker feedstock compared to two different gasifications. So let's say waste to syngas for oxo and waste to syngas for methanol, and also compared then with energy recovery. So let's say what we are seeing here in this case, this is the climate change impact. And we can see that the pyrolysis, hydroprocessing, and steam cracking now together to producing the light olefins are producing for us, this amount of climate change impact. And when compared to gasification, depends which route we go, can be a little bit different. However, they are in any case much more beneficial compared to energy recovery. So we can now look at the credits that we are getting, for example, for producing the cracker products, or for producing the The syngas productions or methanol feedstock, methanol plant feedstocks, we will see compared to the amount of the heat that we may get from the plants and also the electricity. We can have a sum up of the climate change impact in these cases, which shows that gasification might be a little bit beneficial compared to pyrolysis. Depends, of course, on which feedstock it is there and what will be the downstream of using the syngas. But in any case, they are close with each other and they are all far away from incineration. This is a very important point that I would like to mention here. I would like to conclude my talk here. Chemical recycling is complementary to existing mechanical recycling, but there are so many various and abundant resources of plastics which cannot be recycled mechanically. We have pyrolysis and gasification as two main high temperature processes of chemical recycling processes for mixed plastic recycling, and we have enormous amount of plastics available to be recycled in all ways. So there won't be any, let's say, internal war between pyrolysis or gasification because they are different materials, which in any cases, there will be some suitable for any of the technologies available. We have lots of different methodologies, assessments for the future sorting and recycling. There will be hard to have numerous dedicated specific plastic sorts. However, it is more feasible to have several mixed plastic fractions, which are comparable in terms of polymer and contamination contents. And the heteroatom contaminations, recovery of them and upgrading of the chemical recycling products will be one of the most important challenges in terms of resources and costs and design of the plants for the future. Thank you very much for your attention and looking forward for your questions and the discussion.
Yeah, thank you very much, Salar, for this, let's say, deep dive into research on very hard to treat waste streams and the comparison on incineration, so recycling versus incineration. I will pick this up again to the audience. So many people joined since the beginning of this webinar. If you have questions, please put them into the Q&A chat. The speakers will try to answer them during our meeting, and in the very end, we will have a Q&A session of at least 30 minutes where we also can answer questions. All right, so this was about incineration and alternative technologies. We will now, in the next 3 presentations, go deeper into technologies, and after collection of waste, everything starts with advanced sorting. So the next speaker will be Rickard Jansson from Svensk Plaståtervinning in Sweden. He will talk about Site Zero and the next step closer to circular economy for plastics packaging from households. We will have a look at advanced technologies there. So Rickard, again, the floor is yours.
Thank you, Dieter. I will pick up the presentation. Hopefully you see the correct or the presentation slides right now.
It's okay.
It's okay, thank you.
Perfect.
So a very brief introduction to Svensk Plaståtervinning or Swedish plastic recycling. We are a privately owned company owned by the Swedish plastic packaging industry through a different business associations that gather the plastic packaging value chain from material suppliers to brand owners who need to use packaging for their products. And these brand owners, they have the extended producer responsibility in Sweden, since we have such a EPR scheme or EPR legislation since many years. They have the legal obligations to provide a system that can take care of the plastic packaging after use from the consumers and to finance that system. So we are owned by the packaging industry, but they are also our customers indirectly. When they put the packaging on the market, they need to pay packaging fees, and parts of those packaging fees goes to financing the operations that we have. And since 2018, we have a new sorting plant in Motala in the southern part of Sweden, and that plant was we did large investments in that plant last year, and now we call it Site Zero. I will come back to that. But we have some growing challenges of household plastic packaging waste, as you may be aware of. One part is that there is trends showing that we have increasing amounts of plastic packaging being used in for different purposes, but mainly due to a more globalized trade, which requires more packaging materials to protect and store or keep a lot of food products and other products from degradation. And to fulfill the different packaging functions, the packaging industry has developed a lot of different packaging materials based on plastic, but that also means that we have different plastic types in different plastic packaging products. So for example, a PE film based on polyethylene is a different grade of polyethylene than a bottle made of polyethylene or even PET. So we have different types of plastics, but also different grades of plastics, and in some to provide some functions like a high barrier plastic film, you need to often combine different polymers in the same packaging to increase the for example, the oxygen barrier of the plastic film. You need to combine different polymer types to meet all the different functions that the packaging needs, and that leads to a very complex packaging design in the end. And then we are also relying on consumer behaviors. So the consumers can make the right choice and source separate the material, then we will have a better possibility to recycle the material than if they don't do the source separation or and put it in mixed waste, or even if they start to littering the surrounding by putting it into the nature instead. And unfortunately, around in the world, we also have a big lack of infrastructure for advanced sorting and high quality recycling. And all these combined leads to that we have a very big challenge in the efficiency of the plastic recycling chain for the plastic packaging, and a lot ends up in either incineration, as mentioned in the previous presentation from Salar, or even in landfilling if we are missing that possibility, or even worse, that it ends up in the nature. So we wanted to address the lack of this infrastructure by investing in Site Zero. So this is an overview of the plant that we have. It is a previous Electrolux plant to make ovens and refrigerators, and they stopped the production here in Motala 15 years ago. And left a very big building complex behind, 85,000 square meters of industrial facility, which we are now reusing for the purposes of Site Zero. And Site Zero is currently a very big sorting plant that can separate collected household packaging waste into 12 different targeted plastic fractions. And we do that fully automatically with 60 NIR sorting stations. And this brings a total capacity of 200,000 tons of input waste that we can separate into these different 12 fractions. And this can also be translated into that we have a sorting capacity of approximately 1,000 packaging items per second in the plant. And to give even more details about how the plant works, we have this overview picture. So the collected packaging waste comes in bales, and that is for easier transportation. So it is being compressed into bales to then be transported to our sorting plant. And those bales are being put on an input conveyor, and from that point the human interaction stops until the material ends up as sorted bales in the end of the process, where we then can keep it in storage until we transport it to different recycling facilities. The process is mainly designed to separate monomaterials out of the plastic packaging mix. So what the process will do is that it will first separate plastic films from rigid packaging, and the plastic films will be processed in this part of the process, while the rigid plastic packaging will be processed in this part of the process. Sorry, I will point with the laser. So here would be the plastic films, and this part of the process would be the rigid plastic packaging. So the first sorting steps are separating the films from the rigids in this part of the process. The films ends up here and the rigids here. And then we have the NIR sorting stations, which target to separate monomaterials out of the mix. So if we take the plastic films as an example, we have a mix of polyethylene films, polypropylene films, and other types of plastic films. So when we target a monomaterial, we would target one specific polymer. So in this step, in number 8 here, we would target the polyethylene films, and then in the next, and we would separate the polyethylene films. The remaining mix containing much less polyethylene films, but still a mix of different plastics, would come to step 9, where we target the next polymer type, and in this case, polypropylene films. And so we have different sequences where we take out specific polymers. But even with this strategy, we will finally end up with a plastic mix of untargeted plastic films, for example. So let's say that we have these multi-material plastic films where we have combined different layers of films to provide specific functionalities from each layer of the film. Those wouldn't be targeted in the monomaterial sorting because they are a mix of different polymers, and we cannot, and we don't want to target them in a monomaterial fractions. And the reason for that is that the monomaterial fractions will typically go to high quality mechanical recycling, and in mechanical recycling, after washing, you will remelt the plastic into another form. And if you have a mix of different polymers, you cannot separate those polymers from each other in mechanical recycling. So typically you would then end up with a mix of different polymers that are of lower quality than if we could target a monomaterial polymer. So the remaining mixed materials would be then untargeted here, and they would end up in what Salar called RDF fuel typically. So it is the residuals after separating the targeted material in a sorting plant or in a recycling plant. And that RDF material would then be used as an energy source in another process, so in energy recovery typically. But what we wanted to do in this process was that we also wanted to target those remaining plastics, and that's what we do in the step 17 here. So here we have additional NIR sorting, and the purpose of this sorting step is to separate the remaining mixed plastics out of the residues. And the residues are a complex mix of both plastics, but also other types of materials. So it could be textile materials or other waste that consumers have by mistake put in the same collection scheme as the plastic packaging. So if we wouldn't do this last sorting step, we would have still a mix of different materials, and not all of those materials would be suitable to send for chemical recycling in a pyrolysis process or in a gasification process, because you would then send a lot of heteroatoms, as Salah was mentioning, that you want to reduce the amount of heteroatoms, or you would need to upgrade the pyrolysis oil or the gases that are received from the chemical recycling process. So for us, this last step is a possibility for us to separate the remaining plastics after we have taken out the monomaterials in the beginning of the process. And for us, these new material streams are potential feedstocks for chemical recycling when chemical recycling are further implemented in large scale. So just to mention what we currently are sorting, we sort out 10 different mono fractions, and we have 2 mixed plastic streams at the end, and they are one of them are coming from the flexible material, and the other one is coming from the rigid material after sorting. And the next steps for us in the next few years will be to hopefully also have washing and granulation on site. So currently, the monomaterials that we separate, they are sent for washing and granulation or mechanical recycling. And unfortunately, we have very little capacity in Sweden to take care of these materials that we separate. So we still rely on recyclers around in northern part of Europe. And for us, it would be more beneficial from a climate perspective to have it locally, both due to the reason that the Swedish electricity mix is much better than the electricity mix in the grid of Europe. So from a climate perspective, the energy used to wash and granulate the material would be much more climate neutral in Sweden compared to what it is in for example, Central Europe. And the other reason is that we need transports to ship the material to the recyclers. And for us, it could mean 1,500 kilometers to send the material from the sorting plant to the recycling plant. And if we could have the recycling plant next door, we would significantly reduce the amount of transportation work needed. So for us, washing and granulation on site or close by would be beneficial from a climate neutral perspective. But then we have the plastic mixes still remaining. And for us, chemical recycling of these plastic mixes, typically containing a lot of laminated plastic films and other laminates. For us, chemical recycling would be a very good solution. And then even if we do this separation of the remaining plastics by sorting, there are still some mistakes being done by the sorting machines, and that leads to that we will still have a residual fuel or reject that is sent for energy recovery, which potentially contain minor parts of plastics, but also polymer textiles, for example, or paper products with a thin layer of plastics and such. And to treat this reject and still be climate neutral, energy recovery with, for example, CCS or CCU would be beneficial as well. So we are also looking into these possibilities together with partners here in Sweden. The reason to why we prefer to send material for mechanical recycling compared to chemical recycling, currently it's mainly due to that there is a lower energy consumption compared to chemical recycling typically to process the material, and there is already well-established technology with existing infrastructure. So for us, mechanical recycling is the first option when we have separated monomaterials. Chemical recycling, the benefits of that is that we can also treat some of the complex mixes like the multi-layered plastics that mechanical methods cannot handle, or where it results in poor quality of the recycled material. And another benefit is that the chemical recycling typically results in virgin quality materials, so it is easier to use in some contact-sensitive applications, for example, like food contact materials, where mechanical recycling for a lot of plastic packaging materials will come up with recyclates that could contain non-intentional substances that are not suitable to having contact with food, because there is a risk of migrating substances into the food which we consume. So for some applications, chemically recycled materials could be more suitable to use than mechanical recycled materials. So for us, chemical recycling will be complementary to mechanical recycling, but the advanced sorting is necessary to provide both feedstock for mechanical recycling, but also feedstock for chemical recycling. So for chemical recycling to be effective or cost effective, you would like to reduce the amount of heteroatoms and waste that are not suitable to process in the chemical recycling process, and that is the reason to why advanced sorting is often needed also when you want to send material to chemical recycling. If you start with a very complex mix of waste, and the mix of the waste is typically decided based on the collection systems that you have. And for Sweden, we have two ways of collecting plastic packaging or actually we have 3 ways of collecting household packaging waste, but this picture only shows 2 of them. The third one would be the deposit return system for PET beverage bottles, but they are not included here. In the case on the slide here, we have 2 very complex material streams. One is the source separated materials that are being collected from curbside collection in the next years from the Swedish households. And then we have the possibility to also sort mixed plastics out of the mixed waste that goes to waste incineration. So when the consumers haven't done their source separation and they put it in a mixed municipal waste system, there is still a possibility to also invest in infrastructure that do some sort of pre-sorting of the waste that are on the way to energy recovery to separate the plastic mix out here. And our sorting plant, the Site Zero plant, is designed to handle both these material streams. And what we then do is that we separate these mixed plastic streams to have material streams that are either suitable for chemical recycling or for mechanical recycling. And then we still end up with a minor fraction of rejects due to the mistakes that consumers does in the sorting of the waste. And for us, energy recovery with CCS and CCU will probably be needed to be fully climate neutral in the next years. I will quickly come up with just that the legislative landscape is significantly changing in EU right now with the packaging and packaging waste regulation proposal that is coming, and some things that are very important for the next few years are the improved recycling rates that are needed, but also that materials need to go back into food contact materials, where chemical recycling will probably be a good solution for some of the materials. But high quality recycling is very much targeted by the packaging and packaging waste regulation compared to how it is today, where the materials are not necessary to, or the recycled materials doesn't need to be of good quality to be called recycling, but by the packaging and packaging waste regulation, it is required to provide high quality recyclates that can go back into similar applications again. So for us to turn plastic packaging into a more circular resource, we need to focus on three things. One is the design for recycling to reduce the complexity of what you put into the market. And then you need to collect all the materials through either source separation or the industrial sorting that was shown on mixed waste. And then finally, you need to have advanced sorting and high quality recycling at scale to provide the materials back into new packaging products. I just wanted to also highlight that the Site Zero plant is also well described in a report from IEA Bioenergy, which you can find through this link after the presentation. Thank you. And the questions are answered either in the chat or afterwards. I leave it over to Dieter again.
Thank you, Ricard, and that was a perfect ending of your talk. So I don't need to talk about putting the questions into the Q&A chat, please. Thank you again for having the look at advanced sorting and how it fits into a circular economy system. And we are busy with a lot of information in this webinar, so I will directly, hand over to Marco Tomasi Morgano from Arcus Green Cycling Technologies in Germany. So he is Chief Technology Officer of the company that is running mixed plastic waste pyrolysis. The presentation will be about this. And yeah, please, Marco.
Thank you very much, Dieter, for the kind introduction. It's a pleasure to be here and show some highlights on first 2 years of commissioning of our first industrial scale pyrolysis plant. Before I go into detail with the pyrolysis unit, I would like to remind that pyrolysis is a very old, innovative technology, starting from very old time to produce charcoal. Then we had some hype waves about pyrolysis during the oil crisis as alternative waste to energy, biomass research, and finally today in terms of chemical recycling of plastics. If you see the logo there, it's our association of the chemical recycler technology provider, which I would like to mention. So if you are interested, you can have a look at our website. We are a chemical recycling Europe. Something additional about plastics, because also come the question about which kind of plastic are suitable for pyrolysis. Then let's have a short look on which kind of plastic can be used, what are the additives, what comes into a mixed plastic waste. As you know, preferred polymers are, of course, hydrocarbon-based polymers, polyethylene, polypropylene, and polystyrol. You find in every packaging waste, and these are the largest part. But also in mixed plastic waste and packaging, you will find additional polymers containing heteroatoms like PET, PVC, polyamides, and you will always find them in some amount within mixed plastic. So you need to deal with heteroatoms coming from other polymers. You will also find additives, fillers, pigments, I come back to that afterwards. Plasticizer, flame retardants, and whatever. So you will always have to deal with these additives. And finally, depending on the sector, depending on the waste stream, you will have food waste, biomass, inerts, metals, and a lot of very different contaminants. So backline is you have to deal with contaminants either from non-hydrocarbon polymers, from plastic additives, which are there for improving performances, or from contaminants coming from external parts. But what about Arcus? We are Arcus Green Cycling Technology, the small company based in Germany. We consider ourselves the connecting arc between the waste management industry and the petrochemical industry. We would like to produce and deliver feedstock for the petrochemical industry, which can be used to produce new plastic and therefore to bring the carbon back into the loop. We have been founded in 2016. We have a very strong cooperation with the Council Institute of Technology, where I come from as well. So for me, it's like being back home together with Dieter and Salar. So we have lots of experience on a semi-pilot scale plant. We have our first industrial scale process demonstration unit based in Frankfurt, Main in Germany. And of course, we build continuously our cooperation along the whole supply chain, because it's important to have cooperation starting from sorting or from collection as well, sorting, then on the petrochemical industry, but also with brands as well. And as you can see, we are a very small teams. Here is the executive management, Marcos, Daniel, and myself, and our technical team, Mark and Paulina, coming from KIT as well. So we are like a small family, and Julian as well for business development. We have built an industrial scale plant in Frankfurt, launched in the end 2022, 4,000 ton mixed plastic waste input capacity, up to 2,500 ton pyrolysis oil, full electrical operation plant. We have experience with mixed plastic waste, including PET and also PVC and multi-layer plastic. We have a large offtake contract together with the BASF, which take our feedstock or our pyrolysis oil to generate new plastic. The plant itself has been built, owned, and operated by Arcus. The plant is fully authorized for German. Under German legislation, our pyrolysis oil is REACH registered. It's also certified in terms of ISCC Plus, and very important for this. The company itself is certified waste disposal company, EFB, under German standards. And since this year, we are also certified as letzte Empfängeranlage, which means that we are the last receiving plant, which is very important for the German Packaging Act, which enable us to be part of their recycling quotas. So this is a brief introduction of ourselves, but I would like to give you an insight on the process itself. We take the feedstock from the supply chain. We need a little bit of feedstock preparation, and I'll come back to that afterwards. We have a feeding system. We introduce our mixed plastic waste. We have additives, which we use as a contaminant scavenger to answer a question about how do you fix contamination and avoid to go into the oil or into the off gas. We use a solid carrier, which is used with two main tasks. The first one is to improve heat transfer in an endothermic process. The second and most important one is to keep the system clean, so you don't lose capacity with time coming from potential cooking or blocking in the reactor. We flush the complete plant with nitrogen, which is very important, so that you don't have oxygen coming from air, so you don't have oxidation reaction. Our pyrolysis unit is a continuous process, fully electrically operated. There we generate pyrolysis vapors to a mix of condensable and non-condensable hydrocarbons. We go through hot gas filtration and conditioning unit. Then we recover the liquids in 2 phases. The py oil, which is called Arcus liquid, which is stored in our tank and then brought to our customers. And of course, wastewater, which comes from moisture in the feedstock, but also from reaction of polymers containing oxygen, like but not only that one. After recovery, we have a gas purification unit using sodium hydroxide, water to bring the gas to specification required for gas engine pack, which makes us having the chance of producing our own power for powering the oil plant. What happens to the solids? The solids are get cooled down. The solid carrier is circulated back into the system, while the fine dust is removed, separated, and stored, and then goes off today. As I mentioned, the plant is fully electrically operated. So from this perspective, we are ready once the electrical grid will be more green, let me put it this way, to use the gases in another way and go also for carbon recovery out of the gases. I mentioned we need a little bit of preparation. If you look at this picture, the first one, you see how mixed plastic waste comes out of a sorting facility, very low bulk density, material is not conveyable. So we need a first shredding step where the material is made homogeneous, also very important for the stability of the process, and finally produce small pellets. So we will have sufficient high bulk density, so feeding and the processing will be suitable for our process. We don't need additional separation of specific materials. Short insight on the timeline. We started up the plant in December 2022, generate first oil, then we ran through 2023 in campaign modus, short campaigns with different materials, few milestones, achieving the first 100 hours of continuous operation, delivering the first tank, complete full mass and energy balance with rejects out of mechanical recycling, having a very nice conversion rate. I've done some customer tests, and then go through an update of the permit to improve the efficiency of the process. Then we started 2024 with a very nice achievement, having the very first 1,000-hour long-hand operation with our target feedstock, which is DKR 323, so mixed polyolefins pellet, obtained the certification, had the chance to deliver a few more tanks, and then continuing the bottlenecking of the plant to make it up to full capacity and longer run. So for me, it's very important to mention that pyrolysis is not an established process. It still requires development and the bottlenecking, and we are up to this. So in 2023, we ran the plant, as I mentioned, in campaign. I would say we verify the Murphy law, because everything which can go wrong and will go wrong. So we have huge number of issues, but still we were able in few months to deliver the very first tank, which also was in specification. There are some bullet points there. Will go to startup feedstock, but as you can see, you have to test everything, including the emergency torch, willingly or not willingly. Important is the plant works, the plant is safe, and we can operate it in the long run. But talking about the startup material, at the beginning we have an internal discussion on how to start up the system. You don't want to go immediately with the dirty stuff, so we choose what on paper was a clean material, furniture foils made of PP, so also produce a light oil, low ash content, very nice carbon to hydrogen ratio paper. Then you start up the plant, and then there you have around about 40% inert material. So first problems, and first remind, be careful when you deal with waste management industry. And that brought to massive differences in the design parameters to the plant parameters. So we had to solve some issues, and we were able to do that. But anyway, you need to go through issues you do not have on paper, but you have to deal during commissioning of such a plant. All the issues we had, and we still have some issues, but what we learned, and we are continuous learning, is if you don't operate a plant, then you don't learn much. That's the nice part of operating the demonstration unit. You can be able to operate it for a while. You learn, you make optimization, then you learn again, and then you improve your process. And finally, you can, at least for us, was a huge milestone to get to the very first 1,000-hour operation at once, where we were able to test a lot of stuff and, of course, produce quite nice oil. And we are still doing the bottlenecking continuously to bring the plant at full operation. I mentioned the feedstock we are using. That's our target, DKR 323. You see, composition is around about 85% polyolefins, but you have PET and PA also there. So you look at the nitrogen is below 1%, but still high. You have chlorine, even if the specification says less than 0.5% PVC content, then you look at the elemental content and you have 0.6%, so quite a lot of chlorine. Then you have to deal with this. Ash content is there. You have all the elements you can expect in different amounts. As I mentioned, we use our additive scavenger to block all the contaminants in a solid phase. So this is the way we try to solve the issue of having metals and non-desired compounds in the oil and in the gas. Something again about the feedstock. That is stuff you don't want to see, and that's why it is important for us to have robust equipment, robust process, because we have to deal with waste, and of course you have some runaways in the feedstock. You have to deal with that. But then all this stuff you see here, we have found in our lifter. So after the pyrolysis, you find metals parts, you find stones, you find wires, you find everything there. So again, philosophy, the company, the philosophy of the process is to be robust and being able to deal with this stuff far away from specification you might see on paper. We deliver oil, and we have delivered more than 100 tons of py oil to our customers. That's very happy me with the first tank. Then you see the composition and some specifications, some properties of the oil. What I would like to mention is, for instance, a topic which is a big deal in the discussion, the chlorine content. So we started with more than 6,000 milligram per kilogram in the feedstock. We are able to reduce it by 99.9% in 2 dots ppm concentrate. Nitrogen is also reduced. Oxygen is reduced to very low level. It's not naphtha, but it's close to it. And what's important to mention, the oil, doesn't matter, the feedstock, it's stable, which is very important for our customer. Also, I mentioned about polyaromatic hydrocarbons, dioxins and furans. We measure them continuously. in our operation, or we do measurement of that to ensure that these are far below current legislation. And if you have a look, we also measure quicksilver, we measure polyaromatic hydrocarbons. We always have less than 1 gram per kilogram, so we are talking about 0.something%. Dioxin, PCBs, and so on are in nanogram per kilogram range, which is 3 orders of magnitude below current legislation. So for us, this is not an issue. Contaminants in pyrolysis is an issue related to reactor and process technology and not to pyrolysis by itself as a chemical reaction. Not everything is fine. We got the permission of the plant in 2021, May. In October 2021, there was a change in the legislation related to titanium dioxide. It received an upgrade. So titanium dioxide above 1% and particle size below 10 microns is considered now potentially carcinogene. So you always find more than 1% titanium dioxide in the fine dust or in the solid residue. So we are working on sludging or pelletizing to avoid this risk. We are working on it. This is one of the topic you figure out only when you operate. We move forward. We continuously move forward. So we are expecting exciting months in front of us. We have done in the last weeks some tests for customers. We will come out with the press in the coming weeks. We have dealt with halogens. We have dealt with heavy metal concentration far above what is considered to be suitable for pyrolysis. We are doubling production in the last 6 weeks for first time 2,000 hours of continuous operation. We are preparing the plant for the installation of the gas engines. So we are optimizing the gas properties that use. And of course, as a company, we need to always look forward. So we are reviewing all the learnings we had to start designing the first commercial scale plant. First commercial scale plant will be a scale up this plant by numbering of the reactors with additional economy of scale effect in the peripheries, so on. And of course, logistics is a topic. We are working on it as well with all the supply chain. So this picture of our plant in a Sunday morning where I had to take over the shift. I'm thanking you for your attention and looking forward to question now or later.
Thank you very much for these insights into starting up a plant and running it on real plastic waste. I think that was the story about and the feasibility. Again, there are questions up showing, so please take the time to answer them, and we will pick it up later in our final Q&A session. And as time's running, we will come to the fourth presentation that will be given by Henrik Thunmann, who is professor and division head at Chalmers University in Sweden. It will be about, let's say, it goes further in the process chain from mixed plastic waste to high-value chemicals. It will be about plastics and its cracking, as well as cracking of contaminated pyrolysis oils. Yeah, let's go into this presentation. Henrik, please.
Thank you a lot. So I will start by sharing the presentation. So now I think you have it. So thank you a lot for inviting me and have this presentation. So I will talk about the step, actually where you produce the monomers of it, or how we can produce monomers directly from plastic waste, and also these oils if they are also contaminated. So we have a little seen this before. We have the plastic waste. We have also some advanced sorting. It's how advanced it you can discuss. Then you have, if you look for before, you have the pyrolysis. You have hydrogenation, often taking place in a refinery and then sent to the steam cracker. And in the steam cracker, we have some process that produce your olefins and other gas components, and they are separated in the fractionation units, and that are giving then the olefins and the concentrated gases from which all our plastics and a lot of also our chemicals are produced. Looking at this scheme, at the moment is the steam cracking step that actually puts the limit on how the upstream feedstock would look like. This put a very high demand on the quality, and because it is indirect, or it is directly connected to the fractionation, which allows very, very small amount of contaminants, because these are built for very clean feedstocks like naphtha or pure ethane or propane or butane that are sent into these. The other thing with these plants is that you usually have one of these plants per 10 million inhabitants, using them as a very big consumers. So this plant is placed in Sweden, and it's around produce little more than 1 million ton of plastics or chemicals a year. And to feed this with recycled feedstock, it needs more than 1.3 times all plastic waste in Sweden. So to produce the plastics from the same in a closed loop system, you need around 1.3 times more plastic waste than you produce plastic products, just if you convert all carbon back. So if you want to do this, you have a very limited feedstock that you work with. And so one want to do is that one want to have expand the feedstock possibility and also reduce the cost to go through this. Because also the hydrogenation step, if it goes through the refinery, you start to produce competing products like aviation fuels or other things that are also possible to take out in this route. So the question will be, is it possible to design a steam cracker processes that can handle contaminated charring and ash containing materials and can produce a gas that can be sent directly to this fractionation unit? And charring is that you need to have everything hydrated, because these type of crackers cannot handle unsaturated hydrocarbons, because they produce a lot of char in the process. So looking on this, for those who are not knowing how this process actually takes place, is just metal tubes in where you put the gas, naphtha, ethane or propane, together with steam. You take it forward, you transfer the heat by which you take burners, and you work here in temperature range of 700 to 800 degrees. And then you get out the gas, which you quench, and then you do this separation or distillation of the gases into their pure components. So the question here is that you cannot have these solid walls anymore if you go for this type of more complicated feedstocks, because then all the contaminants and char that is produced will be stuck on the walls. So you need to have a continuous regeneration on this if you want to go for more problematic feedstock. And the question we ask us when we have worked with this is how to create a moving heat transfer surface that continuously can be reheated, regenerated, so you can get away from all things getting on, handling also the contaminants, which is not said here, but also capable of transport ashes and other things from the system in a controlled way. And for this, we, in our work, we propose that we use a fluidized bed system, which actually creates a moving heat transfer surface. This is a picture of a bubbling fluidized bed, which is more than it's around 800 degrees, which actually create this surface. Instead of having the surface or heat transfer surface into tubes, through tubes, we have it from the bed material into the feedstock. And then you take in the bed material heated in one side, which is also reanimated in a neighboring reactor. And then it's where it partly is cooled down and is contaminated when it goes out. So what one to do then? If I look on this contaminants, you can see that if you have carbon lengths, so when you crack down or smash your molecules in your plastics or in any hydrocarbons, you create smaller hydrocarbons. And if we work at the temperature lower than or around 600 degrees or lower, you create a very big mixture of quite long hydrocarbons that is not suitable for the petrochemical industry directly. But also when you come into this longer carbon range, they are also, you have embedded contaminants and also additives or heteroatoms that actually connect themselves into the atoms, creating it very difficult to separate them. And there are a huge number of species as well. But if you increase the temperature, we go down into a range where you also operate the present steam crackers, where you can produce a decent number of molecules that then you can build dedicated separation units for. In this range, you have also stripped off more or less all heteroatoms, or the ones that are still here. It's well defined. So you can create known processes to separate them. Another thing that also coming up here when you do a cracking is residence time. You say that you should increase the time or increase the temperature of the feedstock as fast as possible and then cool it down. And in tubular cracker, you send it in and you have the gas packet is going and hit the wall, and each time it hit the heat transfer wall where it gets heated, and then you continue the cracking process. And you want it only to actually happens once, because then you get the maximum production of your olefins and the valuable products. But definitely in a long tube, you will have a certain amount of packaging hitting the wall several times before every part of the gas has hit the wall once. So here is always an optimization in this kind of systems on how to create this as optimal as possible. And this is why you also say that you want to have a very short residence time in this tube, making that the gas going through this tube I showed you on the other pictures goes with very, very high velocity. So if we then use a fluidized bed instead, we actually drop in here. You have a mix of melt plastics, mixed plastic waste that are melted through an extruder. You don't need to have everything melted, but around 30% you need to have in order to get this tightening and getting the feedstock in. And then the feedstock is dropping down to the surface. You create a reaction zone on the surface of the bed, and then where you produce the gases, and the gas leaves. At the same time, on the surface, you dilute this with the steam that you use as fluidization gas, and then you create a situation where you only heat your feedstock once, as we wanted to have. Because if we start to send up a lot of particles into the gas phase, you will continue the cracking process as you continue the heating of the gas. But the gas itself is a very low heat capacitance, and also it is all the reaction taking place is exothermal or endothermal, which means that you get a self-quenching effect as soon as the gas leaving the heated area. At Chalmers, we have a system that mimics this. It's a 12 megawatt boiler, so it's a real industrial installation. We have that as the boiler is actually producing this heating and also regeneration. This boiler is also equipped, so it is meeting the requirement for a waste incinerator. So here we do the regeneration. We take out all the contaminant and ash components, and in a real process, if you build this, you will send in all your residues into the combustion chamber, taking use of the energy in the system while you decontaminate your system by oxidizing the contaminants before then removing them with the same way that you do in waste incineration today through the ash system. Here you have the bed material going up and then it's circulated, and here we have our reactor. And this reactor can handle, when it was designed for biomass from the beginning, it's going to handle up to 600 kilo of biomass per hour. When we operate it with plastics, we can operate it around 250 kilo of PE or 320 kilograms of PET. The restriction is the hand that we also need to burn out the gases that is produced, or we have to handle the gases that is produced. So, but the reactor itself, if it would be put into commercial operation, it would be possible to convert around 10,000 tons of plastics a year. So this is where we run our experiments. We have run these experiments since 2016. So this is once more where you have this fluidized bed going through. And you saw the other picture of how the melt then dropped down to the surface of this heated surface. And then the gas is produced. And we have tested a lot of material since during this year. Of course, mixed plastic waste of different kinds, pure substances, automotive threaded residue, the residue after the light thread that you saw before. So this is a really nasty product, the Tetra Pak, which is a very advanced packaging with more or less 4 to 6 to 8 layers of different polyethylene just in one packaging together with the cardboard. Textile mixtures, threaded tires, medical waste. And as reference, we have operated also with naphtha. And we can see that we can produce a naphtha cracker that produce the same, operate equally well as the dedicated naphtha plants here that they are today used. We have used it for pyrolysis oil, which is crude pyrolysis oil, which gives very, very good result as well. That so you are not needed to hydrate the oil before going in. We have operated with vegetable oil, tall oil, pitch, animal fat. Animal fat is fantastic, even vegetable oil. We have done crude oil, and we also have done like nylon bags and other things among the different things. And what we get then is that we get a mixture here of all kind of different hydrocarbons as you get in the cracker process. And some of them is valuable, and some of them is more or less be used for heating purposes of the processes or need to be recovered otherwise. The aromatic fractions as well. So we have the olefins and alphens, and also the one rings at the aromatics, which are valuable products then from the chemical industry. This is very similar to what you get into a cracker unit today, even from the pure fossil feedstocks. And we can recalculate them because some of them will be recirculated, and we have some fraction here then where you need to go to synthesis processes if you want to go back with this. This we also see, and this has also been seen as a very feasible, from an economically feasible things to do, actually built in a carbon recovery step into these processes. So if you look on our system from the beginning, if you take the traditional pyrolysis to meet the steam cracker, what can we do then if we introduce this more robust steam cracker into the petrochemical industry? Is that we can expand dramatically the feedstock. We can go down in the sorting effect, maybe still some what can call it advanced, but not advanced on separating different plastics. Pyrolysis is, for many decentralized system, a good options to send this pyrolysis for the steam cracking, but we can also take the plastic fractions directly. So, if we conclude this, we present to replace fossil feedstock at scale. We need to introduce more robust cracker processes into the petrochemical industry. Otherwise, the amount of feedstock will be too limited. We have shown that fluidized bed system offer a viable and robust solution, and it's proven at semi-industrial scale that this can work or will work. And we have ever experimental evidence on that the demonstration demonstrates that this type of system performs equally well on naphtha as conventional naphtha cracker, while also handling a wide range of solid and liquid-based feedstocks. For commercial processes, depending on local condition, it will be beneficial to use solid plastic waste or crude pyrolysis oil. The pyrolysis oil does not require to be hydrogenated or decontaminated beforehand, which expand the range of usable feedstock and simplify also the decentralized pyrolysis processes. So we are a big research team at Chalmers doing this, and you will get with a handout, you get available literature you can look on, so you can look on what we have done. And we have a big number of companies and funding agencies funding this system processes. So thank you.
Thank you, Henrik. Also to you for keeping the time scale and frame and giving this broad information on that process. Yeah, thanks to all speakers once again. We're now entering the Q&A session, and I know that a lot of questions had already been answered in the Q&A chat. The only one is Henrik that didn't have the chance to answer anything because they're just showing up, these questions. So let's go into discussion using the Q&A questions which have not been answered so far, and I suggest to simply start with some questions I picked out. I will start with Salar again, and probably one question that was of specific interest, if I find it again. And this was about chemical recycling as a process to clean waste streams from contaminants, so specifically hazardous substances which are included there. So there were several questions even. So what happens to hazardous substances in the pyrolysis process? Would they end up in the gas stream and not in the pyrolysis oil? How are they dealt with?
So maybe I just gave an explicit answer to this question regarding the point of the conversion is the key. So if we have some hazardous material, we have to take a look first of all, what are we talking about? It can be brominated flame retardants, which then some kind of brominated hydrocarbons may be produced during the pyrolysis. We are also talking about some contaminants which are existing in the plastic waste by itself. First of all, high temperature processes converts most of the hazardous material to other materials. So this is basically the important point. The conversion is the key. We are able to convert many of the hazardous material which already existing in the plastic waste into some raw materials. This is the first of the point. And the other point is that we are also in the same time producing some hazardous material in the high temperature processes and conversions. The key is here how we can convert them further to other raw materials. For example, when we have brominated flame retardants or we have chlorine in PVC containing plastics, then they can be converted to raw materials like HBr or HCl for the further processing. Or they can be also binded into the residues by producing salts like calcium chloride, calcium bromine, and they are not hazardous anymore. This is one of the points. Biogenical wastes, biogenical hazardous material are in any case just decomposed after the high temperature. So we are explicitly talking about chemical hazardous material, which then by upgrading and by post-processing, they will be converted to raw materials for the further processing.
Mm-hmm. So it's not that they end up in the gas stream and finally leave the process without being destroyed, but they can be destroyed and heteroatoms can be released, collected, or even converted. Are there already processes that recover flame retardants, so bromine or chlorine or something like this as raw material?
For bromine, there are no established process at this moment in the industry in that way of like bromine recovery from brominated materials inside. For chlorine, there are established materials, but not in the context of petrochemical industry. But it is possible to collect, let's say, wash out the HCl or chlor-containing materials in the way to bring them back to the cycle of, let's say, chlorine for itself, because there are also some material which are energy intensive to produce them as a pure chlorine. So there are also other impurities existing, but the point is when we are talking about chemical recycling of plastics, we are dealing with many impurities which are not existing in the crude oil. So basically in the refineries and petrochemistry, there are not established processes to purify them, let's say to recover them and to concentrate them somewhere. But there are some other cross sectors to the other industries which deal with these contaminants or these raw materials based on which point of view you have or from which endpoints you look at them. And I think this will be the key point for the future of chemical recyclings in petrochemistry to cross various industries together in that matter.
Thank you. Yeah, I step over to Richard. So you presented the Site Zero plant with its sorting capabilities. There was a question on advanced sorting, of course, so the capabilities, but it was in the direction of how much of the sortable material still ends up in incineration, and probably what will be the outlook in the future. So can we sort anything and process it mechanically or chemically, or what is your, let's say, view of the future on the role of incineration? but also today, if you start up the plant, how much of what you can sort can also be used and what will end up in incineration?
Yeah, so if we first discuss the performance of the NIR sensors or the sorting machines that are actually being used, because it's not typically the lack of performance of detecting the material correctly, but there is a mechanical process to sort the materials by air guns that are shooting on the material at the end of a conveyor belt, and depending on the size of the object and how easy it is to eject that material by air gun, it will significantly impact on the sorting performance. But typically for plastic packaging items in the range of maybe larger than 5 centimeter up to 35 centimeter or so in size, the typical performance on a well-designed packaging would be somewhere between 90 and 95% of hit rate on that object, which means that you potentially lose then 5 to 10% into the sorting reject of the same object. But if you have a smaller object, the sorting performance will be significantly reduced. So if you are below 5 centimeter in size on the object that you sort, it will miss that object much more than you do when you have larger than 10 centimeter, for example. So you could end up with 0.0% in hit rate on the smallest object. So you have a wide range of sorting performances depending on the size of the objects. That is one thing. But in our sorting plant, what we have seen is that for some materials that we have monomaterial sorting for example, LDP, we can reach up to 90% in hit rates in general on all those objects that we classify as polyethylene films. While for other materials such as fragile polystyrene, for example, it is crushed easily, generates a lot of small pieces, then the sorting performance is really poor on the NIR, so maybe down to 30% in sorting performance only. So there is a wide range, and then coming back to the question, how much is being left into the sorting reject, that would then depend on what is being put on the market, the material mix that you typically that enters into the market, and also the design of those packaging. So, for example, I saw that we will come back to another question around black plastics, but so I will not touch upon that. But depending on the design, you can significantly also affect the sorting performance. So, for example, if you have a material where you add a lot of attachments to that packaging format. So let's say that you have a bottle with a full-sized shrink sleeve and a cap of another material, then the NIR will target the surface for classifying the material. So if you have a lot of attachments that are covering the full surface of the material, then the sorting performance will also be affected. So a lot of different things will impact the sorting performance. That is what I can answer, but in the best cases, we can reach up to 90% of hit rate on the materials.
So quite a good quality. Now that the chemical recyclers are still missing because they're not on stream so far, or we have just seen one today, would this improve the situation? What do you think?
So if chemical recycling can accept a very heterogeneous mix, I like the idea from Henrik Thurman. You can put almost anything into the process and it will work almost, at least, but or it will work to some point. So then we could have a very aggressive sorting. We don't even need to sort it. Then you could put potentially anything into it. But at some point, I think that sorting will be needed to provide some materials that are suitable to process anyway, because you don't want a lot of metal objects and such inside, and then you need to do some sort of sorting. But you could have a much more aggressive sorting, and then you would increase the hit rate on the materials that you target, with the risk of also introducing more of contaminants that you don't want, because with aggressive sorting you risk to also eject materials that you don't want. So, but there is also always a sorting optimization work needed in the sorting plant to either achieve a high purity material, then you often miss more of the objects you target, or you can accept a more aggressive sorting with the consequence that you also get more impurities into the sorted materials. But chemical recycling potentially would be at that scale where you could have an aggressive sorting in the end of the sorting process and take out the remaining plastics, which we do in the sorting process here in Motala.
Yeah, thank you. So it makes sense to step over to Marco now, because I go along the chain. So back to pyrolysis. Yeah, there was, if we stay with that quality topic, one specific question on pyrolysis was, are there substances that are persistently difficult to deal with? So anything you would not like to have in the waste you put into the pyrolysis plant, Marco? And yeah, is it necessary probably to eco-design products in such a way that these substances do not appear anymore? Can you think about that?
Yes. Depends on which kind of substances we are talking about. Yeah, I discussed the presence of titanium dioxide, which essentially is a pigment, it's a white pigment. So you can try to remove or eco-design as much as possible. I guess eco-design is a part of the solution. Mechanical recycling is a part of the solution. Chemical recycling is a part of the solution. And incineration will still be a part of the solution. I don't see a silver bullet in the whole industry, so all of them will be part of the solution as well. I think eco-design is the first step. You can try to remove whatever is not necessary for performance or specific properties or qualities, but there is a limitation as well. So that's the case for titanium dioxide, but that can be the case also for flame retardants. You will need flame retardant for specific application, so you can't remove flame retardants. It depends on which flame retardant you will use. We see moving from brominated to phosphorus flame retardant in the future, so it will become a topic in the future, for instance. But you still need flame retardants. What about PFAS? I will remove them as much as possible, but probably there are some applications where you cannot remove them. So it's a mix, yeah? And pyrolysis or chemical recycling cannot take everything. Yeah? It has own limitation. Some can be solved upfront through sorting. Some can be solved by post-processing or upgrading. But it will be a part, because it can deal with some specific contaminants that cannot be dealt by sorting or by mechanical recycling. So eco-design is a part of the solution, but all of us, I guess, is a part of the solution. It's a complex industry, it's a complex sector. You have very complex and different applications, so you have to deal partially, at least, with all of these problems, and can be done only by the whole supply chain.
Yeah, thank you for this comment. Yeah, question to Henrik on the cracking of plastics. So the cracking process then that can deal with mixed plastic waste. So one question was, are there any existing fluidized bed crackers in Europe? And probably add to the question, if we regard the cracking process you presented, can it be integrated into existing crackers or cold sections of crackers or something like that?
Yeah, if you look on this type of processes, it's replacing cracker ovens, and you need to have the fractionation unit. The fractionation unit is an extremely heavy investment. So this type of technology only can do if you can build it in large scale. And this means that these units need to be in the range of 100 to 200,000 ton material per unit in order to be economic. And that is why I try to emphasize the volume of material that really need to go here. At the moment, they are not fluidized bed cracker available. The largest one is the one that we have here. But this development is, we do it with one of these multinational petrochemical companies, but they are at least 2 or 3 parallel development of other multinational petrochemical industries going in this type of direction. So this is, you have different pathway. At the moment, we are at the largest scale, and this scale is, as I said, the plant can be, if it would be in production unit, is 10,000 ton a year. This is too small to put into to a petrochemical system.
Okay, thank you for clarification. Just one other question from my side. So regarding the heteroatoms you have in the plastics and the cracker products, which should be free of heteroatoms,
yeah.
How do you get rid of nitrogen and other contaminants that are in the feedstocks?
Yeah, as I said, it's what you do here when you go up to this high temperature is that you push them into known substances, and that is coming back also why you need to have scale. And if you are at scale and have known substances which are limited in the amounts of them, in number of them, there are cleaning procedures to take away them. So you push out, for example, nitrogen, you put into ammonia. Usually you don't produce so much NOx. Mostly ammonia will be taken out. HCN will be taken out if it's produced. That is the main two. And then you also have to have strategies to take out these small contaminants of NO, which then otherwise will have this gum explosion in the cold boxes, which you need to handle. But these are technologies for this, and they have been in present before for cold gasification, and when you did this for cool substances in the past.
All right, thank you. So the basic advantage of chemical recycling is to put things into small molecules that you can separate and by this clean up the wastes.
Yeah, and the cleaning and the separation need scale. Otherwise, you cannot do it economically.
Thank you. Okay, I go the other way around. So back to Marco. Question that showed up several times. Who are the uptakers of the Arcus pyrolysis oil? So what's the use of the pyrolysis oil? I don't know if you want to answer this, but I saw the question, so I put it.
I can answer this very easily. We have a press ad almost 2 years ago, common press together with BASF, quite a large chemical company, I will say. And you will see the product out of our pyrolysis oil in their C-cycled products. So the way they do it is their own business, but through the ISCC Plus certification, we can prove on paper that we take waste, we produce the py oil. What BASF does is to produce products out of this waste-derived py oil. We have other contracts, but the BASF is known, so we don't produce fuels. That's the point.
Probably in that, I mean, your production is quite small, as we heard from the last presentation, compared to the market or the demand. So it's just kind of starting up pyrolysis. There was a question, another question on scaling up of such a pyrolysis unit. So how would this work?
Yes. So our pyrolysis reactor is at its final scale. So the 4 kTA per pyrolysis reactor is the final one. We will scale up by numbering and modularization of the plant. So we have a pyrolysis reactor plus electric furnace will stay this size. We will number them up. The upstream, we will scale up the downstream, and then you can achieve economy of scale. So by numbering and modularization, you will scale up. The most of the costs are not in the core of the process, but around the peripheries, in the logistic, are in the storage and so on. That's the way it will work.
All right, thank you. Ricard, another point you already mentioned was black plastics, and there were, I think, 2 questions on this. So the sortability of black plastics was one thing. So what are the sensors capable of, or would the sensor technology probably change in the future? And I would add the questions, what are the uptakers of black plastics then? So what will they be used for?
Yeah, so the challenge with black plastics are that the most common pigment that is being used in black plastics are carbon black pigments. And carbon black absorbs all NIR light. So when we do the sorting, we don't see the black objects because the sensor is missing them due to that there is no reflection of NIR light from these black objects. So from a sorting performance, the black objects will have 0% in hit rate in the sorting if they contain the carbon black pigment. Packaging designers today, they are adapting to the design guidelines that are given from different organizations, where carbon black pigments are often pointed out as unwanted packaging materials. And they instead change to other dark pigments, even black pigments that are based on something else than carbon black, and that doesn't have the same poor sortability on the NIR sorter. So some big brand owners are putting other black materials on the market that are sortable by NIR. But coming back to what do we do with the the carbon black containing plastics? They are rejected by the NIR machines, but at the end of the sorting process, where we sorted out the mixed plastics, we have another technology implemented, and that is a laser technology that detects the same object by laser. And when the NIR doesn't see that object, we interpret it as a black object and take it out anyway. But then we don't do it based on the plastic type. We do it that we see that an object is passing by. So we don't get it sorted by the different plastic types. We get a mix of black plastics together with other mixed plastics. And this fraction is one of the targeted fractions for chemical recycling. But if chemical recycling is not implemented, the other option would be to use a kind of mechanical recycling, where you mix the plastics together and get a mixed plastic recyclate based on mechanical recycling, where you need to probably add something to reinforce the material into it. So one possibility is to make thick-walled plastic products out of it. This is typically called downgrading in the recycling businesses. But I know that one of our off-takers is making pallets, for transportation purposes out of this material. So that is one possibility, but there are several different possibilities to make thick-walled products like park benches or other things out of it.
How do you recycle a park bench then?
Yeah, that is difficult. That goes typically to energy recycling. So it's a very short-term way of recycling the material, and it is still a linear way of doing it, because you typically need to have secondary products made, and that secondary product will be typically energy recycled after a few after a few years. So it's not a circular way of recycling, I would say.
Yeah. Thank you. That brings me to probably a last question. We have 1 minute left. So Salar again, you presented comparison of, let me remember it, a pyrolysis and steam cracker based route for, I think, the worst waste you can imagine. So a shredder light fraction from cars, and compared it to gasification, if I got it right. So what's better then?
This is a very challenging question, and it is, of course, very feedstock dependent. From my point of view, in the future of chemical recycling, both pyrolysis and gasification has to be available, and both of them will be used. Depends on the contaminations existing in the feedstock, and also depends on the depends on the products that we want to produce. This will be totally different which routes they will go. This is, of course, very important. What we have been compared to incineration, pyrolysis with steam cracking compared with gasification and syngas preparation may have almost a close climate change impact. But of course, in this study, the rest of the value chain has to be also taken into consideration, which will be for steam cracker products, the polyolefin production, and for steam gas products will be then the methanol production or carboxyl oriented basic chemicals and so on. So this will be again another topic that the full LCA to the final product has to be considered. But from the point of the recycling, both of them has to be available regardless if each of them is some % better than the other one.
Okay, thank you for commenting on this. So it probably is a similar eco balance. If you take the avoided burdens into account, it's difficult to balance. Yeah, but probably economics might decide about what is a good way. All right, thank you very much. Thanks again from my side, and I think also I can speak in the name of IEA Bioenergy for sharing this webinar. There was a lot of participants that put a lot of questions, so thanks to all the audience here at this point in time. Probably you as the speakers can still answer questions in the Q&A chat such that there is a feedback. Yeah, again, thanks. And with this, I would like to end this webinar also. See you all. And
thank you.
bye-bye.
Bye.
Thank you. Bye.